Square roots today, but we're actually going to add in higher ordered roots. So we'll have cube roots and fourth roots, and we'll talk about the different meanings there. First thing though, what does it mean if you talk about the square root of 4? All we're looking for is the square root of 4 means what number squared, since it's a square root, equals 4. Well, we know that 2 squared is equal to 4, so square root of 4 equals 2, the number that is squared. So you want to use that same logic for a cube root. So that's what number cubed equals 8. Well, we do know some perfect cubes. Hopefully you remember that 2 cubed is equal to 8. So that means the cube root of 8 is equal to 2. All right, I want you to take a second and think about the next one. Okay, so we're going to look at the parts of a radical. I'm guilty of calling anything with that symbol a square root. If there's not a number written here, it is a square root. It's an understood 2. But when we start writing numbers here, those numbers are called index. An index, that tells us what value we're looking for. A cube root, a fourth root, a square root, if there's nothing there. The entire thing is referred to as a radical. The inside number is called the radicand. Radicand. And the symbol itself is actually called a radical symbol, not a square root. All right? So when you see that sort of check mark symbol, that's a radical symbol. All right, so let's look at some problems. Most of this first group is pretty basic. We know the square root of 64 is 8. And we are looking for real numbers, right? Hopefully you realize that 5 cubed is equal to 125. So we know that the cube root of 125 is 5. Another way of finding these, just like we factored on the other, if you don't know that, you could factor the 125. 81, you may not know this one. So 81 would be 9 times 9, 3 times 3, 3 times 3. Just like for square roots, we look for sets of 2. For fourth roots, we're looking for a set of 4, or what number to the 4th power equals 81, or sets of 4 of something. Well, there's a set of 3s, or 3 to the 4th equals 81. So the 4th root of 81 is 3. That's an equals, right? Here, when we take the square root, we know how to do this now. We know that that would be 12, and that would be an I. But the question asks us for real roots. So the actual answer here is there are no real roots. Okay. We'll kind of come and go, so you need to pay attention to directions, whether we're talking about the imaginary solutions or not. On this one, hopefully you recognize 27, but if not, 9 and 3, 3 and 3. I have 3 3s, and everything else is gone. The fact that it's negative tells me that these have to be negative. So when you take the cube root, you can get a negative, because we know negative 3 times negative 3 would be a positive 9, but times another negative 3 would actually equal negative 27. So with odd index, it's possible, with an odd index, it's possible to take a root of a negative number and get an actual value, a real value. Back to this one, it's an even index. That means I need to have 4 things multiplying. So negative times negative times negative times negative would never give me a negative number. So this one is a non-real. Again, we could do the whole imaginary thing, but they ask us for real. And the last one on this group we're going to look at is this one. Again, it's negative. So I know I'm going to pull out a negative number in my answer. This one is not a perfect cube though, so we are going to factor. and 5 will go into that 27 times. And hopefully you recognize 27 is a perfect cube, but if not, you can break it down. We have a set of 3s, so that's a -3 on the outside, and the 5, just like with our roots, the 5 would stay inside. So I've got -3 times the cube root of 5. Right, so when we're dealing with variables, remember square root of square root of x squared gives us that absolute value. On square roots, we have to worry about that. Actually, on all even index, if you have an even index, any index 4, 6, 8, then you have to worry about absolute value. So problems like that are going to look like we're going to break the 52 down, 2 and 26, 2, 13. So I know I have a pair of 2s. That'll go outside. And I'm going to go ahead, leaving myself some space for my variables, and that 13 will be left, just so I don't forget to do that. Square roots, you're looking for sets of 2. How many sets of 2 x's can I make if I have 6 x's? Literally, all you're doing is dividing the index, which is an understood 2, into the 6, so that's an x cubed, right? You're doing the same thing with the y. What I do when it's a square root, I know if it's an even exponent that I'm going to just take half of it out, divide it by 2. So I'm going to pull that 1 off of this, make that be y to the 4th times y. Here's my y that's staying inside. And then I take half of the y to the 4th, so that's y squared. Now I do have to think, because it's an even index, I have to think about absolute value. So if it comes out to be an odd exponent, I have to make it be absolute value. If it's an even exponent, it's going to be a positive answer anyhow, so I don't need to include it. It does not need to be an absolute value. For an odd index, first thing you need to recognize is there will be no absolute value. And then you just treat it the exact same. We're going to factor, unless you recognize perfect cubes. So maybe half of that, 27. I know 27 is a perfect cube, so I'm going to bring that out as a 3. So inside of my cube root, make sure you're writing that index if it has one besides 2. And the 2 will stay inside. This time you're doing the same thing. You're dividing by that index. So how many times will 3 go into 9? Well, 3 times. Evenly, no leftovers. So no y's left inside. And 3 goes into 4 just 1 time. And that leaves a remainder of 1, so you have 1x left inside. For the 4th root, you're doing the same thing. Hopefully you recognize 625, but if not, we could break that down. We could even do 5 and 125, 5 and 25, whoops, no 2, 5 and 5. So I have 4 5s, but 625 is a number you need to start addressing, not start learning. I do not have a number to leave inside my radical because that is a perfect 4th root. 4 will go into 6 1 time, and there's 2 x's left over. 4 will go into, the index of 4 will go into 8 twice, so I get y squared. This is an even index, so I have to think about absolute value. Y squared is always going to be positive. That x is not necessarily, so the x needs to have absolute value. Lastly, well, actually we have 2 more things. These we're solving. You've been doing this for a while. Since it's a square, we're taking a square root of both sides. We know that'll give us absolute value. Hopefully you realize that's 15. We'll write our piecewise formula where we get x if x is greater than or equal to 0, negative x if x is less than 0, which means I get x equals 15 and I get negative x equals 15, which gives me x equals negative 15. So my 2 solutions are 15 and 15. For the cube root, I am going to take the cube root, and I can take the cube root of a negative number. It'll just give me a negative answer. And 64 is a perfect cube, I hope you remember. That is 4. And the nice thing here is I do not have to worry about absolute value, so that will just tell me x equals -4. And lastly, we're going to do a little bit of multiplication and dividing. We'll expand on this tomorrow. But remember, when you're multiplying, the outside pieces multiply and the inside pieces multiply. I am going to go ahead and try to simplify the 96 and the 245 first, though. Those are fourth powers, so I'm looking for sets of 4. So when I simplify those, I will just simply start factoring, however makes sense to you. And that'll be, do 4 and 12, 4 and 3. Alright, so 4 2s. I know I will get a 2 on the outside, along with the 4 and the 3 that are already out there. 3 and 2 can't do anything. Let's go factor this one. 5 goes into that 49 times. 7 and 7, so that's not going to do anything. And I can't make, even between these, I can't make a set of 4 anythings. So inside my fourth power, I'm going to leave a 2, a 3, a 5, 7, and a 7. You could go ahead and be multiplying some of that back if you'd like. Outside I've got both of my numbers, and then I'll have an x and a y left. So final answer, we're going to multiply these, so that looks like that's 24 xy. Fourth root, and we're going to multiply all of that back, so that's actually going to be 6 times 245. That's going to be 3, 6 times 4. I believe that's 1470. Right? Last thing we're going to do, we've got a multiplication and a division, a little more basic here. These are cube roots, so I would still try to simplify. I know that 8's a perfect cube, so I can make this be 2 cube root of 2 times, and this one 6 times 9, so 2 times 3, have a set of 3's. You might have factored that differently and got a 27, so that'll be 3 cube root of 2. Again, outside pieces multiply, cube root, and inside pieces multiply. 4, of course, would factor to be 2 and 2, but that's only 2 2's, not 3, because we have an index of 3. So there's your answer. Last one, when you have a cube root, if both pieces are inside the cube root of the fraction, both pieces of the fraction, you can simplify that fraction. 6 and 8 will both divide by 6, so I will divide both by 6 and get 1 and 8. Then that's going to separate into the cube root of 1, cube root of 8. For today, they're both perfect cubes, so that can become 1 over 2, and I'm finished. Tomorrow, we'll expand on that.